foundations of logic and the proof, and we will start by something called the propositional logic. So what we mean by propositional logic? So our discussion always begins when we say about an introduction about the basic building blocks of logic, which are propositions. But what we mean by a proposition? Basically, a proposition is a sentence. It's a declarative sentence. That is a sentence that declares a fact that is either true or false, but not both at the same time. The proposition could not be true and false at the same time. So example of a proposition: the moon is made of green cheese, which is false. Dublin is the capital of UK. We wish, but this is false. Toronto is the capital of Canada. This is true, yeah?
No.
That's false. So 1 plus 0 is 1. This is basically a false statement because 1 plus 0 equal 1 today and tomorrow. 0 plus 0 equal 2. That's a false proposition. So all these propositions are false propositions. Now the following are example of what is not a proposition. When you say sit down, this is an order, not a proposition. It does not have an outcome to be true or false. Do your exam and you tell me false. That's meaningless. And then what time is it? This is a question and it's not a proposition. X plus 1 equal 2. This is not a proposition. You know why? Because I don't know the value of x. So this is a calculus object. This is a linear function. This is an equation. So I don't know what the value of x is, so I cannot judge whether the result would make the result of this equation to be 2, so I can judge and say this is a true or false. X plus y equals z. Again, this is a linear equation. I don't know the value of x, I don't know the value of y, so I could not find or judge the value of z. Now with the propositional logic, we need to know how we can construct a proposition, how we can make one out of nothing. So we need 3 things. The first one, we need letters to denote those propositions, and normally we use the letters P, Q, R, and S. If you are not happy with those letters, you can use something else. The second thing to construct a proposition that you would need is the truth value, because a proposition is true. Once the proposition is true, we denote it by the letter T, which is true, and if it's false, we denote it by F, which is false. Now we turn our attention to the method of producing a new proposition from those that we already have. We have some foundation now to use in order to build a proposition. So the new proposition is called a compound proposition, which is basically formed from existing proposition using logical operators. We all know that there is something called in programming, in Python, if not X, do something, right? Have you write this as a Python statement before? Now this is what we call negation, which means that we have P, a proposition, and the negation of P denoted by not P, and this is the statement. Always we translate it in English to be, it is not the case that P, and the proposition not P is read not P, and the truth value of the negation of P is not P, is the opposite of the truth value of P. Which means, if I have any statement, and I call this statement P, and this statement, let's say, the moon is made of green cheese. P is the statement that the moon is made of green cheese. Is that true or false? False. Not P that statement, not that case that the moon is made of green cheese is true. So the negation of any statement If any true statement is false, the negation of any false statement is true. I will give you now example. So the negation of a proposition B is denoted by not B and has the truth value as follows. If P is true, not B is false. If B is false, not B is true. Take the following example. If B donates the earth is round, then not B donates it is not the case that earth is round. Or you can simply say the earth is not round. So the first statement is false. And then not B value will be true. Another example. Find the negation of the proposition today is a Friday. Is today Friday?
No.
So this is false statement. And it's you can express it in simple English. And the solution for this, the negation of it, it is not the case that today is a Friday. So in simple English, today is not a Friday or it is not a Friday today. You can use any combination of those. In the exam, when I ask you, give me the negation of the statement, it is not a Friday or today is a Friday. All you need to do is just to say it is not the case that today is a Friday. Okay? So this is the first foundation for us to use to make a compound proposition. The second one, we can make like we have one statement saying today is a Friday and the other statement saying I don't have to go to work. Those are two statements, P and Q, and they are both are a proposition. We can combine them and we can make a compound statement of a proposition, like the if statement you use in programming when you say if x greater than 1 and x or y greater than 10, do something. The same will apply here when we combine the proposition together to make one single statement, and the connectives we use are and, or, XOR, and NOR. I know you did this in the digital circuit last semester. I know you did this in Python. Now all we need to do to apply and to use the same connectives in order to make a good proposition. So the first one is called conjunction. Here we have P and Q, both are a proposition. Let's say the first statement, which is P, is referring to a statement like today is Friday, and the Q is another statement, it is raining. You will simply say now, P and Q, does it today Friday? And is it raining now? So both conditions are what?
False.
False. So false and false equals to false. And this is the rules of and in the truth table. So the conjunction of P and Q donated by P and Q and is the proposition that both P and Q must be true or false. So the outcome of the truth table will be true or false. Let us take an example. The conjunction of a proposition P and Q could be denoted by the truth table showing in the diagram, where we have P, T, Q, T. And true and true is always true. True and false, it's always false, because we need both value to be the same in order to have one true outcome. False and false is false, and false and true is false. Now let us take an example. If P refers, now P is just only one single statement. And instead of saying the whole statement, I'm just saying I'm giving a variable. It's just like in Python when you declare a variable and you say P equal this statement. I am at home. Q is, it is raining. If I say P and Q, the truth table of this value, when you combine them by a conjunction, this means you are saying P and Q, which is I am at home and it is raining. So you combine two statements together by and. That's all. Another example. find the conjunction of the proposition P and Q, where P is the proposition today is a Friday and Q is the proposition it is raining today, and the truth value of the conjunction. Okay? How you would combine them? Today is a Friday and it is raining today. Now, today is not a Friday, which is false. So the first statement P is false. It is raining, it's not right now, so this is false. So false and false is?
False.
False. Now, the second foundation that we can use to build a proposition is this junction, which is the OR, guys. Don't make the names just misleading you. When you have P and Q, both are a proposition, the disjunction of P and Q denoted by P or Q, and it is the proposition where we have the conjunction P or Q is false when both B and Q are false and is true otherwise. Here the case is different from and. In OR, what we can really have, we could have a true outcome from this junction once we have only single true value in the truth table. So true or true is always true. True or false is always true. False or true is always true. False or false is always false. Example, if I say I am at home and Q now referring or declaring a variable for the statement it is raining, I could say P or Q which denotes I am at home or it is raining. It's meaningless, but this is how we combine them using the disjunction. Now, beside having the OR, with this junction, there is some more attributes, which is the NOR and XOR. I will explain. So that disjunction is true when at least one of the two propositions is true. That's how disjunction works. Now, a student who have taken calculus or computer science can take this class. You see, the outcome, even from looking to this as a simple English, it's always true. So anyone could take the class if he is already a computer science student or he have taken this course. Now, once you are talking about exclusive OR, the disjunction is true only when one of the proposition is true. That's the exclusive OR, because it's exclusively true once there is only one of them true. But a true XOR true or true exclusive OR true is false. Now, if you want to make exclusive OR for the above statement, students who have taken calculus or computer science but not both can take this class. That's why it is exclusive OR, where we don't need both statements to have a true value. I need one of them. Only those who take one of them. And the definition 3 previously used exclusive OR. And none of you just noticed why I was saying the conjunction P or Q is a false when both B and Q are false and is true otherwise. If you look to the truth table here, that this is the normal OR. And here we are talking about exclusive OR, where we need at least one of the two statements to be true. To define this now, if you have P and Q, both are a proposition, the exclusive OR of P and Q denoted by the symbol is the proposition that is true when exactly one of P and Q is true and is false otherwise. I will stop now for okay, so the next definition now is going to be about conditional statement. which are the if, else, then statement we use every day in programming. Now, if you have P and Q, both are propositions, the conditional statement P implies Q is the proposition that if P, then Q, which means the first statement should be true in order to make the second statement is true. And here we are talking about more about an assumption and a result of that assumption. I will explain this in details. So the conditional statement is false when P is true and Q is false, and true otherwise. In the conditional statement, P is called the hypothesis, the proposal, the assumption that you propose at the beginning of any mathematical theory or the premise, and Q is called the conclusion. So always, if you want to have a true conclusion, the hypothesis should be true. Sometimes the hypothesis would propose something and the conclusion is still to be true. I will explain this in the following example. So a conditional statement is also called an implication of something else happened. So look to the example. If I am elected, then I will lower taxes. So we have P, which is pointing to the first statement. P only stand now for if I am elected. Now Q is the other part, which is basically I will lower taxes. Now let us take the truth table of them. The first truth table, which is the implication of them, I am elected, I will lower taxes. So I am elected true, I lowered the taxes is true, so the outcome P implies Q is true. P goes to true. So the hypothesis was true and the implication of that or the conclusion was true. Now look to the second one. I have not been elected, but taxes get lowered by somebody else. I don't care. But this is what happened. Okay? So I have not been elected, so this is false. And the taxes has been lowered by somebody, and this is true. F false implies true, give the result as true. Because here there is a conclusion happen to be true based on different condition, but not this condition. But there, and it is true. Now, and I am not elected and I haven't lowered the taxes, both are false. I have not been elected and I have not been lowering the taxes, so this is false. False implies false, which is true, because here the hypothesis is false and the conclusion of the hypothesis is false. And this is where you will find most scientific experiment happening. All computer science experiment is there. When you have a hypothesis for your master thesis, you need to prove or disprove that hypothesis. And you can simply say in the conclusion of your thesis that this hypothesis does not stand for the following reasons. So the hypothesis was false and the conclusion was true. Or you propose a hypothesis and you prove it. You did an application or a software to prove that your hypothesis was correct. And you say the hypothesis was proven, so that was true. And now this is my conclusion for the following reason. And I will say true implies true, or implication of P was true. Even if you say my hypothesis was wrong, I was wrong, guys, I could not manage to prove it on the code, then that's false hypothesis, and the result, the conclusion from a false hypothesis was also false. So the whole outcome of this, false implies false, which is a false proposition, which is a true proposition, which is true. More example about this conditional statement, because I know it is something you don't really digest very well. So let P Maria learns discrete mathematics. This is only one single statement. And Q, Maria will find a good job. So here I'm giving a proposition. If you do this course, you will be a research scientist in Google. This is my proposition. And I give a hypothesis that my course is a mandatory skill for you to accelerate in your career path. Now let us see how we can interrupt this in simple English. If you express this statement as P conditionally goes to Q as a statement in English, you will find any of the following is true. If Maria learns discrete mathematics, then she will find a good job. It's an if statement, guys. Maria will find good job. See, this is the result, the outcome of my hypothesis when she learns discrete mathematics. And finally, for Maria to get a good job, it is sufficient for her to learn discrete mathematics. The first one is true and goes to true. The second one is true and goes to true. And the third one is true and goes to true, and so on. Besides having those conditional statements, we have something or more degrees about those conditional statements, how we can classify them. So we have the converse, the contrapositive, and the inverse. And we can form some new conditional statement starting with a conditional statement, starting with a simple statement. If x greater than 10, then print hi to all DT249 and DT255 students. That's a simple if statement. Okay? But we can change how this if statement by the following reasoning. So there are three related conditional statements that occur so often that they have special names. The proposition P implies a Q is called the converse of P implies a Q. Now the contrapositive of P implies a Q is the proposition that not a Q implies not P. If I prove a hypothesis to be true and the result of the hypothesis was also true, the opposite of that is always true, because if the hypothesis was not proposed, I would not get the same result. An example, if I said, if you study discrete mathematics, you will get a job in Google. If you don't study discrete mathematics, you will not get a job in Google. So the not here, the contrapositive, is the negation of both parts. Now the proposition not P implies not a Q is called the inverse of P implies a Q, and we will see that of these three conditional statements formed from P implies a Q. Now some facts about those level of conditional statements. Only the contrapositive always has the same truth value as P implies a Q, Q implies P. Now when two compound propositions always have the same truth value, we call them equivalent. And this is equivalent to the same statement if I say today is not Friday and it is not raining. So this is a conditional statement, right? Both are true, and this implies that the result is true. Combining this to another statement, if you study discrete mathematics, you will get a nice job, as well true. And true combined with a true is always true. So a true fact with a true fact both represent a one single unity of a true. When two compound propositions always have the same truth value, we call them equivalent. And we will study the equivalent later on, and we will give you more examples about them. The converse and the inverse of a conditional statement are also equivalent. Now this is a little bit confusing, and we need to make a truth table for that in order to understand what we mean exactly by saying the converse and the inverse are both equivalent in their truth table value. When you convert them to a truth table value, you will find them they are equivalent. So neither is equivalent to the original conditional statement, but you will find that converse is not equivalent to the original conditional statement, or inverse is not always also conditional or equivalent to the original conditional statement. Let me now take example. What are the contrapositive, the converse, and the inverse of the conditional statement? The home team wins whenever it is raining. The solution for that is really simple, guys. We here just playing with simple English. We just need to change how this statement look like based on the truth table values we studied. Because Q whenever P, this is how conditional statement works. Do something whenever the condition I propose is true. So when Q whenever P is true is one of the ways to express the conditional statement P implies a Q. And the original statement can be rewritten as if it is raining, then home team wins. So I'm giving the hypothesis to be the raining, and the implication of having a rain, that the home team will win. The converse of that is if the home team wins, then it is raining. And the inverse, if it is not raining, then the home team does not win. It seems really stupid just saying those guys, they will never win any game if it's not raining. And this is the inverse of the conditional statement we just described before. So only here you will find that contrapositive is equivalent to the original statement, as we are going to see in the next examples. We will take more examples about each one of them, and we will study them carefully and slowly. Now, we need now to start working together in a group of 2 students to try to practice what we have learned today. And this is kind of reflective learning, guys. So, which one of these sentences are a proposition, and what are the truth values of those that are propositions? So you have 1, 2, 3, 4, 5, 6 statements, and I want you just to work with your colleague on them. So as we said, the answer for this activity, the first one is false, the second one is false, the third one is true, the fourth one is false, and the number A is not a proposition. This is an equation, and the last one is an order, so this is not a proposition. The next thing we want to discuss is what we call biconditional statements. You will find in this course that conditional statement is a little bit harder than biconditional statement. And this is really a strange thing that you would experience. With biconditional statement, we have a definition that we have both a statement, P and Q, and both are propositions. And the biconditional statement said is the proposition P if and only if Q. And this is where you will find most of mathematical theory use. You will say, for example, the biconditional statement P implies Q is true when P and Q have the same truth value and is false otherwise. A biconditional statement are also called implications, because this means that the hypothesis leads to the conclusion and the conclusion leads to the hypothesis. Let us take an example before we start wondering what is this. If you have P and Q and both are a proposition, then we can form a biconditional statement by saying P if and only if Q. So the truth table of this biconditional statement, and I want just to point here a very important note for you guys. Those truth table, we have to learn them by heart. We have to recall them in the exam paper. We have to know how they behave, how they function. And there is no difference between the truth table we have for and or in digital circuit, in digital logic, and this one, because digital logic is built upon this science. So when we have the case of biconditional, we have P and Q. If true leads to true and true take us back to true, then the outcome is true. So true is if and only if true. Now the second one is true and it gives us the outcome false, but false would not lead us to true, so the outcome is false. False leads us to true. Never. You never have a false fact leading to a truth. So a lie will never be a true fact. So false leading us to true, this is false. But now a false fact leads to a false conclusion is a true. And this is how logic work. If you have a false theory, this is give you a false conclusion. And if you have a false conclusion based on a false theory, which means altogether compound will be a true proposition. Now more example. Sometimes B implies Q has the same truth value as P implies Q, and Q implies P. Combining them together, and if you do the truth table for all of them, you will find that this statement is true. And sometimes we call it if and only if, and can be expressed in many mathematical theory or textbooks as IFF. Example. If you take the statement B to be the statement you can take the flight, and let Q be the statement you buy a ticket, then P if and only if Q. Here what we are saying, that you buy a ticket, you can take the flight if and only if you buy a ticket, or you buy a ticket if and only if you take the flight. So this is the translation of this biconditional statement to a simple English. So the implication of this statement is, if you buy a ticket, you can take the flight, which is true. Both are true, so the outcome is true. The implication of this is true. If you don't buy a ticket, you cannot take the flight as well. Is it false? False proposition leading to a false implication, so the whole outcome is true. Example of a truth table. This is how things really look like. You will have a variable, a proposition variable like P, and another proposition variable like Q, and you have the outcome, the implication, which is R, and now you want to find the value for the equation above. This is a simple exam question. This is a typical one. So put on this slide big star with red color, because in the exam I will be asking you to do the same equation. So here you have the value for P and Q, same as what you did for digital circuit when you build the truth table for P and Q, zeros and 1. Now 1 is true, 0 is false. Just replace them with the truth, true and false. So we have P and Q, and we have the value of R. Now what you need to fill is not R. True, not true is false. Not false is true, not true is false, and so on. Now, what is the value of P or Q? Now look to the value of P and Q. True or true is true. True or true is true. True or false is true. True or false is true. False or true is true. And false or true is true. And false or false is false. And false or false is false. Now go back to the truth table of implies and apply in the last row, which is, we need now the result. Once you have true leading us to F, this is F. Once you have true goes to true, this is true. Once you have true goes to F, it's F again. Once you have true implies true is true, and true implies false is false. The true implies true is true. False implies false is always true, because the hypothesis is true and the conclusion is true. False is the hypothesis, and and not R is the conclusion, and P or Q is the theory. Okay, so a false theory leads us to a false implication or a false conclusion. So this is true, and we have now a true result coming from a false theory, which is a true.
According to that slide, that one should be false.
The last one?
Last slide.
The last slide is biconditional. This is
Okay.
this is a conditional if statement. This is if statement. Okay? Do you have any questions about this, guys?
Yeah, what is R? Can you just remind?
It's just a propositional variable.
All right.
I propose its value. I put all these rows myself, and this is the rows that I filled.
Yeah.
Okay? So not R I filled myself, P or Q I filled, and the outcome of them, I take the conditional statement, the if statement truth table, and I apply it there. I look to the truth table and I calculate the outcome of each one of them.
All right, so R you write it yourself.
Yeah. Now let us discuss something called equivalent proposition. We said before two propositions are equivalent if they always have the same truth value. So this is by a conditional statement. Show using a truth table that the conditional is equivalent to the contrapositive. So if we have, for example, P and Q, I fill the value for true and false values myself. So myself, I filled those values. Okay? Now take not Q and take not P. Calculate not P based on the negation truth table. Every time I say the true, not P is false. Every time I say false, not P is true. Every time I say the Q is true, not Q is false, and so on. If it's false, not Q is true. If it's true, not Q is false. If it is false, not Q is true. Now again, apply P implies a Q. Apply the P implies a Q truth table that we have in the previous slides. We have true implies true is true. True is implies false is false. False implies true is true. And false implies false is as well true. Do the same for the negation. When you have not P and not Q, you will end up saying that false implies false is true. True implies false implies true is false. True implies false is true. True implies true is true. Now compare both of them. P implies a Q and not a Q implies not P together. You will find the true here. False, true, true. Based on this truth table, we say both statements are equivalent because they have the same truth value in the truth table. So both statements are true. Now another example. Show using a true table that neither the converse nor the inverse of an implication are not equivalent to the implication. Here we start with something really simple. We take the value of P, we take the value of Q, we do not P and not Q like before in the previous example. Now let us fill the column of P implies Q. We know that it's true, false, true, true by the previous example. And not P implies not Q is true, true, false, true. Now, would be able to match P implies Q to Q implies P? No, because the truth table has a mismatch in the second row here. Here I have false, here I have true, and here I have true. So based on that, we just prove that the converse nor the inverse, they are equivalent to the implication itself. So P implies Q is not equivalent to the converse nor the inverse, based on the truth table showing there. The last topic of today is going to discuss how we can approach a compound proposition based on the precedence of them. Similar to computer programming, when we say precedence of the operators, take the parentheses and then take the star and the division before the plus and minus. We apply the same rule. Not always take the first order. So we always deal with not as a first class entity. We do it first. Then you do and or before anything else, and then you do the conditional, which is the implies, and the biconditional if and only if comes the last one to proceed with. So if you look to the statement P or Q implies not R is equivalent to having a parenthesis P or Q implies not R. If you take if the intended meaning is P or Q implies not R, you can also convert this statement based on the law that we are going to study later on in coming class to a simplified formula. It's similar when you say 5 multiplied 2 plus 2, and then you say this is like 10 plus 5. You take the parentheses out and you put the outsider variable inside the equation. So then the parentheses must be used. One famous application of this science, which is the propositional logic, is translating English to propositional logic, system specification, Boolean searching, logic puzzles, logic circuit, the one we use in computer, and all diagnosis method. And this is an example just to remind you that this is the same of AND gate, OR gate you studied in the last semester. The inventor is basically the negator, the not. When you have P, not P is the inventor in the digital circuit. OR gate is basically the OR, and gate is basically the AND that we discussed. So the inverter, not gate, is an input bit and produce the negation of the bit. The OR gate is basically two inputs, but it takes the equivalent of the disjunction of two bits. AND gate, it takes and produce the equivalent of conjunction of two bits, and this is basically a symbol one. When you speak about compound statement, we are speaking about compound circuit similar to the one here in the diagram. When we have P and not Q, and then we take that value and we make an OR gate, with not R to give you a final outcome result. So here, with this example, we could understand how to employ this logic in computer science and digital circuit, and how we employ it every day in our programming. Thank you guys. This is the end of the lecture of today.